Dr. Ranjani Parthasarathy is a professor in the Department of Information Science and Technology, Anna University. Her area of specialization is computer architecture and networks. One of her special interests is Indian language technology systems. She is actively involved in research in all the areas and has over 50 publications to her credit. She has about 25 years of experience covering both industry and academics.
Welcome to the UGC lecture series in computer science. This is the series of lectures in computer architecture. We have been looking at some basic operational concepts that are there with respect to computer organization and architecture. We have looked at some performance measurement issues. We have also looked at instructions. What we have been looking at in terms of instructions is what are the typical types of instructions: arithmetic, logic, data transfer, control and I/O instructions. And then we also looked at instruction formats in the sense that we looked at what should go into an instruction, that it will have an opcode which specifies the operation to be performed and some operand information. So, these are the topics that we have covered in the lectures that we have had so far. So, in today's topic we will look at a little bit more on using the instructions that we have talked about so far in terms of how these instructions are sequenced. And when we talk of instructions, we have always said that the addresses of the operands are specified in the instructions. So, how is it that these operand addresses are specified? We have a concept called addressing modes which is used to specify when we talk about how the addressing is done. So, we will try to take a look at these addressing modes and how they are used. So, talking of instruction execution. So, what should happen in terms of instruction execution? You will normally have a series of instructions which are available in some memory location or starting from some memory location. So, let us say we have a 3 instruction program segment, okay, a simple instruction program segment where we have an instruction called move A comma R0, then you have add B comma R0 and then move R0 comma C. Okay. So, let us say we are doing something like you moved A to R0, then you are adding the contents of B to R0 and then the contents of R0 are moved to C. Okay. Let us say we have a simple 3 instruction program segment like this. Assuming that these instructions are all 32 bits, which means they take up about 4 bytes, and if we assume that we are using byte addressing, that is the memory is addressed in terms of bytes, then if the instruction starts here, let us say this address here is I, the next instruction would be at I plus 4, subsequent instruction at I plus 8 and so on. So, in terms of a straight line, you could have instructions just specified as a simple straight line sequence, and if you start execution at a particular point, one after the other different instructions will be fetched and then executed and the results will be obtained. Typically what would happen is in memory you will have some area which is allocated for instructions and the data for the program may be specified in some other memory locations. So, when I talk about memory address A, memory address B, C and so on, these are basically memory locations where the data is stored. Okay. So, this is what you would have if you are doing a straight line sequencing of instructions. Of course, the assumptions that we had in this case was that one memory operand is there per instruction, right, as we saw in this case, and that we use 32-bit words and that memory is byte addressable and full memory address can be directly specified in a single word instruction. Remember, this was an assumption that is important because look at what we specified here. Here we have said move A comma R0 and A basically is the address of a memory location. So, this complete address we have assumed can be specified in this instruction. So, given these assumptions, you could have some kind of a straight line sequence like this. Now, let us say we want to have a slightly more slightly more useful or complex program. Let us say we want to add n numbers. So, what could be the straight line program like this? Basically, I know that there are n numbers available at locations num1, num2 etc. up to num n, let us say. Then I would have instructions here, say starting from location I. The first instruction says move R0 to move num1 to R0 and then add num2 to R0, add num3 to R0, okay, and so on. You would go on adding all the n numbers which are available at locations 1, 2, 3 and so on. Okay. First value is moved and then the rest of the values are all added to that register. So, R0 at the end of these n instructions would have the sum, so which could be moved to the allocation called sum. So, if you had this kind of a simple program, it would very easily do a summation of n numbers for you. The only problem with this kind of a straight line program is that if your n value was large, let us say you are adding some 1000 numbers, So then you would have to write 1000 such instructions, each one doing first one doing a move and the 999 add instructions. Obviously it is not a very efficient way of doing things. So what we normally do when we have these kind of situations is that we use what are called as loops. I am sure you are all familiar with this, we have all done C programming and so on, so you are familiar with loops. So what would happen here when we use a loop is that you would have the code sequence like this. What would it be? Again, let us say I have got now I am having this value n, which is the number of elements that I need to add. I store that in a register called R1. So, I have an instruction called move n comma R1 and then I clear R0, basically R0 is made to 0, let us say. Now, then I know that there are these numbers available starting from num1 to up to num n. Okay. If I know the position of the first number, starting from there I can now access the number and add it to a particular register. Okay. So, which means inside this loop what I would need to do is determine the address of the next number and add that next number to R0. Now, this I will keep doing until I have added all the n numbers. Now, the n numbers are available in a register called R1 since I have moved it there. So, what I do now is I will keep on decrementing R1. So, when my R1 becomes 0, I can come out of this loop. So, as long as my R1 is less than or equal to 0, I will keep doing this addition operation. So, typically I will have a program loop here and in order to control this loop I will have a branch instruction over here. So, what is the purpose of this branch instruction? To check whether you have completed the loop, and that is done by means of decrementing, by keeping a count of the number of elements to be added in this register R1 and then I keep decrementing R1 and when R1 goes to 0 I will come out of the loop. So, if the R1 value is greater than 0, so which is why I have a statement here which says branch greater than 0. This basically means that if my branch value was greater than, that is the previous value, that whatever I did now, the operation that I did, if the result of that operation is a value which is greater than 0, then I will branch back to loop and keep doing this loop, otherwise I will come out. So, which means at the end of this loop you will come out, the value R0 that you have where you have been adding all the numbers, that value has a sum which can be moved into the memory location called sum. So, this is what we would need to do. Okay. So, in this case we are using what we call as a conditional branch, and in this branch instruction, if you see in this conditional branch instruction, you will have branch greater than 0 and loop. What is this loop? This loop is the target of this branch. We refer to it as the target of the branch, in the sense this is the memory address to which you need to branch back to. There is now the instruction execution at the end of this branch will go back here and start from this location loop and keep executing. Okay. So, this is what we will need to do. So, now the point to look at over here is we need to have these conditions based on which branches will have to be taken. That is, we are looking at, you can see what we are doing here. What we are doing here is a control transfer. We talked about different types of instructions. So, here the branch greater than 0 kind of an instruction is a control transfer instruction where the control of where I need to execute is being transferred now to this location called loop. Otherwise, you would go on doing things in a sequential manner. So, to break that sequence and move to a different location, we have these branch conditions. Now, and when we do these branch conditions, there are some, when you have these branch instructions, there are some conditions based on which you will branch. So, I need to know how to get hold of these conditions. So, that is the next thing that we need to understand. So, these conditions normally are referred to as condition codes. So, we normally have inside the processor as part of the ALU or associated with the ALU some logic through which you can set these condition codes. So, once the condition codes are set, then using these condition codes we can do the branching. So, the condition codes are referred to also as condition flags or condition code flags, and they are typically maintained in what we call as a condition code register, or it may be just called as a status register. Now, typical conditions that we maintain in most of the processors are the following. You have an N flag which is called as a negative flag. Basically, it means that the previous value was negative. Then you have a Z flag or the 0 flag. Now, this indicates that the previous value, whatever operation took place, the result of that was 0. So, then you have an overflow flag, a V flag. So, this means that the previous operation ended in an overflow condition. You have overflow conditions when you are adding, say, let us say you are adding two numbers and the result is not able to be fit into the register. You have value which is greater than what can be fit into a register, you have an overflow condition. So, this is an overflow situation. The other is a carry. We all know what a carry is. So, in case a previous operation, say an addition, generated a carry, then the carry flag is set. So, these are typical flags that are set. And so there are many instructions which can affect these status registers or set these condition flags. So we say different instructions therefore affect different flags. For instance, there are certain instructions which will set certain flags only, and there are certain instructions which may set all the flags. So all these are possible. So we need to know what kind of instructions set what kind of flags, so that we can use those conditions when we are coming up with the conditional branch instructions or the conditional jump instructions for control transfer. So if you look at for example, let us just take one simple instruction and see how the different condition codes are set. So I am taking a simple addition instruction. So let us say I have a number A and a number B to be added. Okay. So the number A is say I have 1 1 1 1 0 0 0 0 and B is 0 0 0 1 0 1 0 0. Okay. Now the actual operation I am doing is A minus B. So that is A plus minus B. What I need therefore is I need to take the 2's complement of this number B here. Right. So, you have got 0 0 0 1 0 1 0 0, I take the 2's complement of this number which is 1 1 1 0 1 1 0 0, and now since I am doing A minus B, I just need to add this 2's complement to A. So, you can see what is happening here. When I do this addition, this is the number that I get. Okay. So, when I get this number, what do I get here? So, you can see that this generates a carry. Okay. So, the carry flag will have to be set to 1, and since the most significant bit which indicates the sign bit is 1, the S value is equal to 1, and then there is no overflow. So, the V value is equal to 0, and then the actual number that you have, the value that you have here is non-zero, therefore, the 0 flag is equal to 0. So, this is a typical example of how the condition code should be set based on an operation. So, when this operation of A minus B took place, these different condition codes would have been set in this particular manner. Okay, this is what would normally happen. So, like this, depending on what kind of instructions we have, different instructions would set different condition codes. So, the way these status bits would be maintained inside the processor is typically that they will all be coupled with the ALU. So, let us say I have the ALU here, 2 operands coming in A and B, and the some function that is being carried out. So, F is the output. So, what would typically happen is, so let us take for instance these 4 bits, the overflow bit, the 0 flag, the sign flag and the carry flag. The carry flag will be set depending on whether a carry is generated or not. So, let us say we have a CN bit which indicates the carry, that will tell whether the carry flag is set or not. Similarly, the sign bit will tell me whether the sign flag is set or not, and then you will need to do a 0 check, because you will have to take the value of the other bits that we have, see whether that value is equal to 0, and based on that set the 0 flag. And then if there is an overflow, we need to identify that, which is typically done by XORing the Cn and the Cn minus 1 bits, that is the carry and the most significant bit. If the two differ, then we know that an overflow has occurred. So, then we set the overflow flag based on that. Okay, so, this is typically what you would have in terms of the status bits and the condition codes. So, with these condition codes, with this logic available for setting up condition codes and so on, we will be able to get the different conditions set, and once these conditions are set, then we can use these conditions for program sequencing using the different control instructions that we have. So, we will take a short break now and then come back and look at a little more on addressing modes and so on. Welcome back after the break. So, we just looked at how the instruction sequencing is done. Next part that we will look at in this session today is we will take a look at how different addresses are basically specified in an instruction. Okay. So, we come to this topic called addressing modes. Now, this is a very important topic with respect to understanding instruction execution. So, what is this addressing mode? Basically, what we deal with in terms of addressing mode is the following. So, we talk about how to specify the operands, right. These operands could be either in register or in memory. So far what we have been looking at is when we took some examples of instructions, we freely used register locations, memory locations and so on. We have really not bothered about whether it can be specified there or not specified and so on, but that specification is typically done only when we understand these addressing modes. So, which is why we need to understand these addressing modes. So, how to specify the operands, whether they are in register, in memory and so on, and if it is in memory, how do you specify the address? Is it directly specified or indirectly specified? So, these are issues that we look at here. And then of course, we have seen that we use branches and you have to specify the target of a branch. So, how do you specify the address of a branch target? This is another aspect of understanding addressing modes. Next thing that we need to look at is, can we give the memory operand address directly in a single add instruction? We have so far assumed that it can be given. Is that okay, or do we need to specify it in some other manner? So, the different ways in which the location of an operand is specified in instruction are referred to as addressing modes. Okay. So, this is what we need to understand. So, now with addressing modes in place, if you look at our instruction format, so far we said instruction consists of opcode and then operands. So, now we will also look at another factor which is introduced called mode, which will also have to be specified for the different operands. Okay. So, that is something we need to understand. Okay. So, now let us look at the different addressing modes. We will start with some of the simple addressing modes first. The first addressing mode that we will look at is what is referred to as implied addressing mode. Now, we have already referred to this when we looked at different types of instructions, especially when we looked at one address instruction and zero address instruction formats. So, now when we had in a one address instruction format, when we said add memory location and we specified some address, let us say which was specified in some address register. So, this automatically meant that I was adding this value to the accumulator. So, this accumulator here was implied, right. So, whenever we have something implied like this, when one of the operands or one or more of the operands is implied, then we refer to that as implied addressing mode. So, here the accumulator was implied to be one of the source operands as well as the destination operand. Okay. So, this is called as a implied addressing mode. Similar implied addressing mode is also there in zero address instructions. So, for instance, when we had zero address instructions in a stack based architecture, for instance, and we just said add, we said automatically it will take the operands from the top of the stack and top of stack minus 1, add it and store it back on the top of stack, right. So, in this case this top of stack was something which was implied. Okay. So, this is an example of implied addressing mode. Okay. The next addressing mode, which again is a very simple addressing mode, is called as the immediate addressing mode. So, here what we do is the value which is to be used by an instruction, right, that value itself is directly specified in the instruction. Okay. So, this is normally used for constants, that whenever you want to use constants that need to be used. So, we can specify the value of that constant directly in the instruction. For example, I can give something like this, move r1 comma hash 5. Now, normally we put a hash sign in front of it to just indicate that this is a immediate value or immediate constant value that is being specified. So, this means when this instruction gets executed, what would typically happen, what would happen actually is that the value 5 would be stored in the register R1. So, you can see why it is called immediate, because the value is immediately available, right, in the instruction itself. Nothing else needs to be done. I do not have to fetch the operand from anywhere. The operand is available directly in the instruction itself. So, from the instruction I can take the value and store it in the register R1. Okay. This is called as immediate addressing. Then we have another addressing mode which is called as direct addressing. Okay. So, in this direct addressing there are again two variations of this, one called register direct addressing and the other called memory direct addressing. In register direct addressing, what we do is we specify which register holds the operand. For example, when we say move R1 comma R2. Okay. So, R2 let us say is the register which holds the operand, that value has to be moved to R1. Okay. That is assuming that my source operand is the second one and destination operand is the first one. If your format was such that this is the source operand, this is the destination operand, it would mean that R1 value is moved into R2. We normally try to use the convention, normally try to follow some convention. So, let us say for this discussion we will assume that R2 is the source and R1 is the destination. So, R2 value will be moved into R1. So, why do we call this register direct addressing? Because the operand, the register address, right, which register I am referring to, that information is directly available in the instruction. So, it is called as register direct addressing. The next variation, which is memory direct addressing, now that we have looked at register direct, you can easily guess what this is. So, what would happen here? Here we specified the register number. So, similarly when we say memory direct addressing here, we will be directly specifying the address of a memory location. So, we refer to this as direct addressing, or sometimes it is also referred to as absolute addressing. So, because we are actually specifying absolute memory addresses. So, if you have something like this, move R1 comma 100, this means this 100 here, remember it is not a value, but it is the address of a memory location. Okay. So, if you compare this with the immediate addressing that we had earlier, in the immediate addressing we said move R1 comma hash 5, typically this hash indicates that it is a immediate value. So, whereas here when we look at memory direct addressing, we said move R1 comma 100, there is no other sign specified before this. So, this normally is used to indicate that it is a direct address. So, this would mean you will go directly to location 100, get the data from there and put it into memory location into the register R1. Okay. So, this is what would happen in the direct addressing mode. Now, when you say direct addressing mode, obviously it means that there is something called indirect addressing mode. So, now we will look at what that indirect addressing is. So, when we say indirect addressing, what we do here is that you specify a memory location, right, and which holds the address of the memory location that actually holds the data. Okay. Let me just understand this with an example. Okay. So, let us say I have an address register 101. Okay. So, this register 101, this is the address that I am specifying. So, in my instruction I will say move R1 comma the value which AR is pointing to. So, 101 let us say. So, now what happens, 101 is a memory, is the address of a memory location. Now, this, if you look into this memory location, you will find something which is some value there. This value here is now the address of the memory location which actually holds the data. So, let us say I had a value 0104 over here. That means this is now pointing me to the memory location 104, and this 104 has the actual value 110A, which is the data that needs to be taken out. Okay. So, you can see how there is an indirection that happens over here. So, which is why we call this as a indirect addressing. So, what is this indirection? You can see that you specify an address, and that address a memory location, that memory location has some contents, right, and these contents point to another memory location, and the contents of that memory location is the actual data that we need. Okay. So, this is referred to as indirect addressing. Okay. Now, when we talk of indirect addressing, just as we said I can specify a memory location, it can also be a register which holds the memory address that holds the operand. So, for instance, if I have something like this, right. So, I have an instruction say move R1 comma say in brackets R2. I am using the notation that when I specify it like this within brackets, it indicates that this is an indirect addressing mode. And how do I interpret this? I interpret it in the following manner. R2, I look at the contents of R2. The contents of R2 let us say has a value 1021. So, now this 1021 is the address of a memory location which has the data. So, I look at this contents of the register R2, pick up this memory address from there, and then from that memory location the data which is there let us say is 500. So, this 500 will be the value that is moved into the register R1. So, this is what will happen when you have a register based indirect addressing mode. So, it could be memory based indirect addressing or register based indirect addressing, both modes are normally used. The more common method that is typically used in many of the instruction sets is this register based indirect addressing mode. Now, there is another variation of this kind of an indirect addressing mode also which is used, which is called as auto increment addressing mode or an auto decrement addressing mode. So, what we do here is we do pretty much what we do in an indirect addressing mode, but we also do something more extra than that. Okay. So, what we do here is when you say auto increment, this would mean that I would let us say I did move R1 comma R2 plus. Now, I have the same notation as I used earlier within brackets R2, but I have one plus which is added after that. The meaning of this plus is that I would access the contents of this location R2, right, 1021 is what I would have accessed, and 1021 let us say had 500, therefore, that value 500 will be stored in this register R1, and after that this register value R2 will be incremented, which is what the plus indicates. So, R2 now will become not 1021, but 1021 plus 1 or 1022, or it could be 1021 plus 4 if your memory locations are all in 4 bytes, it will become 1021 plus 4. So, it may become 1025, right. So, you will specify, this is called as an auto increment addressing mode. So, why auto increment? Because you are automatically incrementing this value register once you have done the move operation. Similarly, we have an auto decrement addressing mode. So, you say minus again in brackets R2. Again remember that I have note that I have put a plus on the right here and a plus and a minus on the left over here. The reason is that here what we normally do is you first do a decrement of the register R2 and then you access the contents of that register. Okay. So, we call this as a post increment, and this is normally referred to as a pre decrement. Okay. These are two variations that we have of the auto increment and auto decrement mode. Sometimes of course, you could also have the other way around, but this is the normal convention. We will see why this is more convenient when we actually look at different types of instructions and how they are used. Okay, so but remember that these two are special instructions which not only allow you to access contents of a memory location, but also automatically increment the register address, so that next time if you want to access another location which is another address which is located exactly next to that, automatically you can do it. Okay. So, this is the auto increment, auto decrement mode of addressing. Okay. Next we have the addressing mode which is called as relative addressing. Now, what is this relative addressing? So, here what we do is, this is normally used when we are talking about finding out the target address, especially in the case of branch instructions and so on. So, here what we do in relative addressing is the following. The effective address that you want to calculate, EA stands for effective address. This effective address that you need is calculated as the sum of the value which is there in the program counter plus a relative address. Okay. So, which is why it is called as a relative addressing, that is the value that you have is specified relative to the PC. So, let us say we have something like this. So, let us say my program counter value is 2 and this relative address that I am specifying is a value 100. So, now what I would be looking at is PC equal to 2. So, I will take the PC value 2, add this 100 to this. So, when I add these two, I will get a value of 102, and now this 102 is the address of the memory location from which I have to fetch my data. Okay. So, this is called as relative addressing. But as I said, normally this relative addressing is not used, is used more to get the branch target addresses rather than to fetch data, but this could also be used. You could also use this to fetch data. So, which means you need your so you will have to say where your data is located relative to your PC, your program counter, which holds the current instruction address, okay, whichever instruction is currently being executed. Okay. Now, what is to be noted here is, normally with respect to this program counter, you are adding this relative address, right. So, this relative address could be either positive or negative, normally specified in 2's complement. So, which means I could look at a value which is less than the PC value, I mean PC value's address, or greater than the PC value, so positive or negative could be used. The next addressing mode that we need to understand is what is referred to as indexed addressing mode. So, here what we do is, here we have a another register called the index register, a special register which is used as an index register, plus another relative address can be specified. Okay. So, here the effective address is calculated as index register plus relative address. So, let us see how this will work. So, here again we do something similar to what we did in relative. Only thing here is, we have this index register, let us say this has a value 2, and then I have relative address specified in another register, let us say which has a value 100. So, both these values are added. So, I get 102 as my effective address. So, 102 is what I will look at to find out what my data is. My data specified here is 110A. So, 110A will be the data that is taken out when I use this kind of an addressing mode. Again, remember that the value that you have here, the index register value, could be positive or negative. So, it can be normally specified in 2's complement, and this kind of a index register based addressing is also very useful with auto increment or auto decrement kind of addressing. So, remember we just talked about auto increment and auto decrement. So, this auto increment and auto decrement, when used along with this index register, this indexed mode of operation, will actually give you a lot of flexibility in addressing the different data which are located one after the other, especially when you are looking at an array of data being accessed. You will find that combinations of these addressing modes make the access very efficient. Another variation of the same type of adding two registers to get at a effective address is called as a base addressing mode, or base register addressing mode. So, what we do in this case is, we have, instead of an index register as we had in the previous case, now we have a base register, and then you have a relative address that can be specified. So, here we do base register plus the address register value are added together, right, and then that gives you the effective address, and then the value which is there in that effective address is the data that is taken out. So, here normally what we do is, this base register would normally point to the beginning of an array. So, that this relative address, if you keep varying this value, you will be able to access different elements that are there in the array. Okay. So, this base register kind of addressing is used when we are accessing successive elements of an array. Here again, this relative address just specified in some register could be either positive or negative. So, you could go either from the base register up or down, both are possible. Okay. So, these are the different addressing modes that are used commonly, okay, in many of these many of the processor architectures. Many of the instruction set architectures use either all these addressing modes or some combination of these addressing modes. So, to summarize, we can take a look at what we have done so far. There are two topics that we have covered today. One is instruction sequencing, in where we looked at how condition codes are used, and then we have looked at these different addressing modes: direct, indirect, immediate, indexed, register, base plus based and or based addressing mode, or base plus index addressing mode, and then auto increment and auto decrement addressing modes. Once you understand the basic idea of these addressing modes, then we can look at different combinations of these to see how effectively they can be used for accessing different memory locations for different data structures. Questions as usual for revising today's topics. Question number 1, when is a conditional code set? What is it used for? Question number 2, what are the different addressing modes? Question number 3, identify the addressing mode and calculate the effective address in the following instructions. Add R1, R2, R3, load R1, 100 of R2, store 90 of R2, R3, R1, add R1, minus of R4. You can try and see what this store 90 of R2, R3 means. We have not really mentioned this particular addressing mechanism here, but you can check out what it means. We will look at that in another class. Thank you.